Alright, everybody, we're gonna talk through the first part of chapter 7. And since we're getting into a new chapter, there's a cool picture here of a place called Calico Rock, Arkansas. This is a picture of the White River, and then there's this really cool, bluff place you can walk to, this overhang, get cool pictures and stuff like that. I guess it's not really a hike. You can kind of drive to this rock, overlook it, and then walk out onto it and get pictures and stuff. We did this in the fall, and so you can kind of see the leaves were turning in the background. But I will warn you, if you go to Calico Rock in the fall, every time we've gone, we see tarantulas. And I hate spiders, big ones, like with a passion, so I would not get near to this, but our friends were with us, and they wanted to get a picture with it, and yeah, it was terrifying. So anyways, just be warned, if you go, you might see those. Okay, we're going to get into chemical reactions. We've been talking a lot about chemical reactions, how to write them, how to balance them, how to classify them, how to then take things like mole ratios and molar masses and calculate stuff with a chemical reaction. But now we're going to talk about energy that's involved in chemical reactions. And then in later lectures, we'll talk about rates and equilibrium. So today we'll mostly focus on energy. And I have two pictures here. The picture on the left is a picture in Russia. This was a long time ago. I think it was back in the 80s. And there was a nuclear reactor that exploded in a city called Chernobyl, Russia. You can look it up on the internet and read all about it. Released tons and tons of radiation into the air. People had to evacuate. It was an awful situation. But you can see the aftermath of a reaction where a lot of energy was associated. I mean, it left a huge hole in the ground. And then a picture on the right is another picture involving energy. Obviously, something's catching fire here. The tire and friction on the ground is releasing a lot of heat, energy in the form of heat. So there's a lot of different reactions or pictures I could show you that are associated with energy. These are just two things, and I would like for us to think about energy in the human body. And so we're going to make a list of some of the main forms of energy. Since I'm doing this kind of late in the day, I will probably forget a form here or there. So this won't be an all-inclusive list, but we've got some pictures here, and I would love for you to pause the video and see if you can write down what are some different forms of energy. I'll get you going. So for example, if you look at these flasks and you've got these different solutions, you might be able to tell these flasks contain chemical energy. Okay, so chemical would be a form of energy. All right, so see if you can think of a few others, and then come back to the video and see how many we got the same. I'm going to continue on. There's solar energy. There is nuclear energy. There is thermal energy, like what we saw in the race car picture above. There is mechanical energy. There is electromagnetic energy. Okay. There's definitely other types. I'm going to just kind of leave it at this. I just want to get your mind thinking in the direction of there's more than one type of energy. So there's just a few examples from my pictures that maybe you can think about. And how does this apply to the human body? Well, what kind of energy does our body use? Maybe from that list, if we go back up, which one would you say the human body uses or runs off of? It's definitely not nuclear energy, right? Maybe you guessed it, but it's chemical energy. Right? And my second question is how does our body take the fuel, the chemical energy we feed it, that kind of like what this magazine says. It says fuel your body for optimal performance, okay? That fuel is the chemical energy we feed it. And how does it generate energy? So what do we feed our body? We feed it O2, oxygen, when we breathe. And we feed our body food, right? And this is what contains chemical energy, the food we eat. And so think about what processes in our body work with oxygen and work with food. And maybe you realize respiration is kind of the name for the process of how we take oxygen and use oxygen to play a part in turning out energy. And metabolism is kind of the overall sum term for how we take food and metabolize it in our body to generate energy. And what chemical do we produce that encompasses this idea of generating energy? And maybe you guys know it's ATP, okay? So this very much does what we're going to be talking about and how we're going to dig into these chemical reactions and look at how energy is associated with any given chemical reaction. It has a whole lot to do with the human body and making ATP. Now, before we jump into kind of the details of Chapter 7, I want to go back to types of energy because we listed, thermal, chemical, all these different types of energy, but all of those really fall under two umbrella fields of energy, which is kinetic and potential. So kinetic is the energy of motion, and potential is stored energy. Right? And energy can flow freely in between mechanical and electromagnetic and thermal, and it can do so by moving back and forth between kinetic and potential energy. And we're mostly going to be focusing on potential energy moving forward, okay, when we're looking at molecules and chemicals. So just remember that potential energy is stored energy, okay? Think of it like water behind a giant dam. That water holds a lot of potential energy, or water at the top of a waterfall before it actually falls and becomes kinetic, moving water, kinetic energy. That water holds a lot of potential energy, okay? That's one example, one way to think about potential energy. All right, so I have this question here. Drink of water. And the question says, how do we know if a chemical reaction will occur? So just because you can write and balance any chemical reaction doesn't mean the reaction's going to happen. For example, look at this one. This is AU, which is gold, plus H2O, water obviously, makes AU2O3, so that is a gold oxide, and it makes hydrogen gas. Now I want you to think, if I had a gold piece of jewelry, like a necklace or a ring or something, and I dropped it into a cup of water, are you going to see a chemical reaction? And the answer is no. So we can write and balance a reaction for this, but just because I drop a piece of jewelry into a cup of water doesn't mean it's going to start like bubbling and making hydrogen gas all on its own. okay? And the reason for this is energy determines if a reaction will occur spontaneously. Okay, now in this reaction above, you're not going to get a spontaneous reaction. So what do I mean when I say spontaneously? The word spontaneously in the world of chemistry, it means that once a reaction gets going, it will happen all on its own, and it will go to completion with no external help. Okay, and gold and water is not going to react spontaneously. It's not going to get going and then run to completion all on its own. We would probably have to do something to this reaction, like add heat or something like that, to get it going, okay? So hang on to this word spontaneously. You'll also hear me use the word favorable or unfavorable a whole lot in different portions of Chapter 7. Reactions that tend to be spontaneous tend to be favorable, okay, from a chemistry standpoint. So that may not make a whole lot of sense in your head right now, but just kind of hang on to that idea and we'll come back to it. And then we're going to read the statement below. It says, if the products have, and the blank here is less potential energy than the reactants, the reaction will occur spontaneously. Okay, so you might be thinking, well, how do we know if a reaction is going to occur spontaneously or not? How is energy determining that? And it all has to do with potential energy. If the products have less potential energy than the reactants, the reaction will occur spontaneously. Okay, so, and I always like to give an example here when talking about this of like a kid eating candy. So remember, we've talked a lot in this class about how things want to be stable. Remember when we talked about valence electrons and everything wants to tend towards stability, okay? So the more potential energy you have, the less stable you are. The less potential energy you have, the more stable you are. You might want to write that down. The more potential energy a chemical or something has, the less stable it is. And the less potential energy it has, the more stable it is. So think about a kid who has eaten some Halloween candy. You know what? We're that family that still has Halloween candy in our pantry. My daughter asks for it like every night. And if I let her eat some Halloween candy or any candy, she's going to have some energy, right? When they eat sugar, when kids eat sugar, they have a lot of energy. And so then she's probably going to, be really energetic, running around. She might be loud, and when she's done running around and, getting all that energy out, then she might be a little more calm or sleepy or want to lay down, right? So think of it that way. The more calm a child is, the more stable they are, right? And the less calm they are, the more sugar or energy they have, the less stable they are. So I don't know if that helped make sense to you, but sometimes I like to throw that example in, and that helps this whole idea of more and less potential energy make sense to people. So the amount of potential energy you have relates to how stable you are. Okay, so I'm just going to write that word stability here. Okay. Now, before we jump into some of the details, there are 3 factors overall that determine energy and that's in a reaction, and if that reaction is going to be spontaneous or not. So the first factor is enthalpy. Okay. And then the second factor is entropy. And then the third factor is Gibbs free energy. Now, we're going to spend a little bit of time talking just about this first factor, enthalpy. And then probably after exam 2, we'll get into entropy and Gibbs free energy. All right, and I want to bring up too, some of you may be wondering, is this content going to be on the exam? Chapter 7 is not going to be on exam 2. Okay, no material from chapter 7 is going to be on exam 2. So I hope you don't stop watching this video, because you will need to watch it, after exam 2 for sure. But I particularly put this lecture in the schedule before exam 2 so that we didn't, finish material on a Tuesday and then you had to turn around and take an exam on Thursday. So, anyways, moving on with enthalpy. So, what is enthalpy? Well, before I just tell you what enthalpy is and define it, I want to kind of give you a little bit more information. So we will define the word enthalpy in a minute, but let me tell you, let me read this statement to you. It says reactions occur via the rearranging of bonds, right? And we discussed that in chapter 5, that we don't make new atoms or destroy atoms, we just rearrange atoms and by breaking bonds and forming new bonds. So we're going to fill in these blanks just below. Now the first one is the word breaking. Okay, so breaking bonds requires energy, an investment of energy into the chemical to break the bond. And then forming bonds releases energy. Okay, so these are opposite processes, and there's an opposite transfer of energy. Okay. Now, how much energy are we talking? How much energy do we need to break a bond? And the answer is it just depends. It depends what atoms are in the bond, and it depends how many bonds you're trying to break, like if it's a single, double, or triple bond. So let's look at the picture right here with nitrogen and chlorine. Nitrogen is held together, 2 atoms of nitrogen, by a triple bond. And you can see in red here, it shows that, low battery, that it would take 226 kcal of energy per mole of nitrogen molecules to break this triple bond. And this energy is literally going to be absorbed into the molecule to break those bonds, to break it into 2 individual nitrogen atoms. Okay? And for chlorine, though, which is only held together by a single bond, you see it takes a whole lot less energy to kind of come in here and, whoops, okay, what did I do? And break that bond, okay, into 2 chlorine atoms. 58 kcal of energy per mole. And we call this energy, we call it the bond dissociation energy, which is the answer to these blanks down here. The amount of energy necessary to break a bond is known as the bond dissociation energy. And there's a whole table down here where these have all been calculated for different bonds. So people have taken the time. Now this is not an all-inclusive table, but it does show a lot of different bonds between different atoms, single bonds, double bonds, and triple bonds, and the amount of energy related to that particular bond. So if you were going to break a carbon-hydrogen single bond, it would take you 99 kcals or 413 kilojoules of energy. Because remember, calories and joules are both units of energy. Right? Now, I'm pretty sure I give you this table on exam 3. So you definitely don't have to memorize anything on the table. All right, now I want to make a point really quick. I just showed you, we just talked through this figure right up here. But I want to actually look at the reverse process on each of these. If we took 2 nitrogen atoms and bonded them together, we're forming bonds here, forming a triple bond, it would release the same amount of energy that's required to break the bonds, okay? Because we're doing the opposite process. In the top picture, in the top figure up here, we're breaking bonds, but in the bottom figure down here, we're forming bonds. But again, the same amount of energy is associated if you're talking about the same kind of bond. Okay, same idea with chlorine. If you're bringing 2 chlorine atoms together and forming a chlorine single bond, you would release 58 kcal per mole of energy. Okay. And this whole idea, represented by these two figures, is kind of a law. It's not kind of. It is a law in chemistry known as the law of conservation of energy, which says that energy is neither created nor destroyed in chemical reactions. It's just transferred. Okay, and here you can see it's either being transferred into the molecule or out of the molecule. Okay, when we break bonds, it's being transferred into the molecule. When we form bonds, it's being transferred out of the molecule. So the energy required to break a bond is the same as the energy released in making that bond. Okay. Now that I've talked to you about all of that, we can define what enthalpy actually is. So enthalpy, which we abbreviate with an H, is a measure of the energy stored in the reactants or products. Okay? And then as a reaction occurs and goes from reactants to products, we can measure what we call the change in enthalpy. And I'm going to zoom in. We abbreviate change in enthalpy as delta H. You guys remember specific heat and how we said change in temperature in that equation was delta T? Same idea here. Change in enthalpy is delta H. Okay? And that is the difference between the energy needed for bond breaking on the reactant side. Okay, so we break bonds on the reactant side. And bond formation, which happens on the product side. Okay. So, you guys have actually seen this reaction before. This is it's a reaction for the formation of ammonia, NH3. And I'm going to show you this one time how people add up or come up with these numbers for the amount of energy needed for bond breaking or the amount of energy needed for bond formation. You're not actually going to have to calculate this the way I'm going to show you on the exam, on exam 3. But it's good for you to see it one time because in the next few slides I'm going to have some numbers associated with the reactant or the product side, and you might want to, you might be like, where did those numbers come from? So we've got a molecule of nitrogen here, which we know is a nitrogen triple bond. And from looking at the coefficient, there's just, a 1 here, right? So if you draw this out, and I'm not going to write it in the lone pairs right now, we're just looking at the bonds. There's just one nitrogen molecule, and we would have to break that nitrogen triple bond, which we have seen from previous slides is going to cost us, it's going to require an investment of 226 kcal of energy per mole of nitrogen molecules. And then we have 3 hydrogen molecules, so if you want to draw these out, it's going to be, we have to break all 3 of these single bonds so that we can form our products. Okay, now down here it tells you that 1 hydrogen single bond costs 104 kcal of energy per mole. So to break all 3 of these, we'd have to say, well, that's going to cost 3 times 104 kcal per mole. So total 226 plus 3 times 104, how much energy total would we need to break all of these bonds? Could you add that up? Maybe you can pause this video and do that and then make sure we got the same number. Alright, so obviously this is going to be 312 when we multiply all that out, plus the 226 is going to be 538. So that's how much energy total per mole we would need to break all the bonds on the reactant side. And then to form all of our new bonds, if we draw out a molecule of ammonia, it looks like this. And you can see in one molecule of ammonia, you've got 3 nitrogen-hydrogen single bonds. But our coefficient tells us we're going to have 2 of these molecules for every time this reaction happens. So I'll draw the second one out. So total, how many individual bonds are we going to form? And every bond that we form is going to release, since they're all the same bond, all a nitrogen-hydrogen single bond, every single one of the bonds is going to release 93 kcal of energy per mole of that bond. So if you count them all, we've got, I'll just highlight them. 1, 2, 3, 4, 5, 6. We're going to form 6 individual bonds, right? So total, the amount of energy released when this reaction happens and this product is formed will be 6 times 93. All right. Now, I wish I was really, really, really good at math. But I'm just going to calculate this. 6 times 93 is 558 kcal of energy per mole. Okay? So, I'm going to go down to the next slide because these numbers, the 538 and the 558, are summarized down below. Okay, so what we see in this reaction is that 538 kcal per mole of energy is needed for all the bond breaking. 558 kcal per mole is released in the bond formation. Okay, so we're going to have to invest this amount of energy, and the reaction's going to release this amount of energy. Okay, now overall, what will happen is you're going to look at these two numbers and say, well, which one's bigger? And obviously the 558 is bigger. So what that means is that overall this reaction is going to release more energy than it absorbs. I'm going to say that again. Overall, this reaction is going to release more energy than it absorbs. Okay? And now I'm going to fill in these blanks at the bottom. When overall heat is released, delta H, which you guys remember is the difference between the energy needed for bond breaking and bond formation, delta H is going to be negative. Okay, and the way we calculate delta H is we literally, delta H equals the energy absorbed on the reactant side minus the energy released on the product side. So we just subtract these numbers, reactants minus products, and we get a negative 20. Okay, so overall, when this is the bigger number on the product side, delta H is negative. Overall, when heat is absorbed, so if we had the opposite situation, delta H would be positive. Okay. So let's look at another example of a reaction. Here we have N2 plus O2 makes 2NO. And the amounts of energy are listed for each of the bonds. So we're not going to draw out the Lewis structures here and look at those bonds, but here's the bond energies associated with these molecules. And all we have to do is multiply them by the coefficients, all right? So this would obviously be times 1 times 1. And so we would just add these numbers up, right, to get the total amount of heat input, which is going to be 345. And then we would have to multiply this one by 2 since the coefficient is 2. And that one would be 302. So here you can see that more energy is needed on the reactant side. So more energy is going to be absorbed. And the difference is 43 kcal per mole. So 43, when you take the the difference here, more energy is needed for bond breaking than what's released for bond formation. So overall, heat input is needed. And then I just have summarized what we filled in above. So for this reaction in particular, if you did 345 minus 302, you would get a positive 43. Okay? So overall, delta H is positive for this reaction. Whoops. I'm going to scroll down to the next slide. So I'm going to, I've got the same two reactions that we just looked at. This was the first one we looked at, and this was the second one. And this kind of gives you the summary of what their delta H's are. We saw a negative delta H for the first one, and then we saw a positive delta H for the second one. So I'm gonna give you kind of some vocabulary terms. If heat, I'm gonna read this right here. If heat is released and delta H is negative, the reaction is exothermic. We would call this reaction an exothermic reaction. Okay? From the viewpoint of the reaction, since it's releasing energy overall, that's why delta H is a negative. We view that as a loss to the reaction. The reaction is the system, and we're viewing things from the system. Okay, so that's why we call that an exothermic reaction. Down below, since delta H is positive, that means overall the energy or the reaction is absorbing energy. All right, so if heat is absorbed overall, delta H is positive. We call this reaction an endothermic reaction. Okay, and this could be written different ways. You might see a reaction written, and then the delta H is written out beside it, and it's positive or negative, and you could determine if the reaction is exo or endothermic that way. Or people might write in heat. Okay, they might say plus heat on the product side, since overall it's releasing heat. Or they might say if you have an endothermic reaction, then they might say heat on the reactant side. Heat plus your nitrogen and your oxygen is going to give you your product. So whichever side is going to have the higher energy number, you would write heated on that side. Okay, so I have a question. Obviously, we're not live in class, so I don't have a poll for this. But could you look at reactions 1, 2, 3, and 4 below here and tell me, are these endothermic or exothermic? So pause the video, see if you can guess these from looking at how the reaction's written or what the delta H is. All right, let's see if you got them right. So number 1 has heat on the product side, so this is going to be exothermic. Number 2 has heat on the reactant side, which means it is endothermic. More heat is absorbed on the reactant side. Number 3 just shows you a reaction, but with a delta H that is negative. Okay, since the reaction has a negative delta H, this is exothermic. And then number 4 here has a delta H that's positive, so this is endothermic. Okay. So I'm going to pause this video. That's all we're going to cover for today. And after exam 2, we'll pick back up with this material.